Welcome back, everybody. This is our video lecture on section 4.5, Integration by Substitution. This is our second to last video lecture, and this is one of the most important integration sections going forward into Calc 2. So the general strategy here is that we're going to change the integration variable in order to make the integral easier. The way that we're going to do that is by a technique called use substitution. So in part A, what we're going to do is we're going to choose the inside of the function here, 2x plus 1, to be u. And then we're going to take the derivative of that to calculate that we get 2 dx is equal to du. Or in other words, du over 2 is equal to dx. Now I always like to solve for my u and my dx, so my substitution is really easy here. So what I'm going to do is I'm going to rewrite this integral, the integral of the sine of, and now I'm replacing my 2x plus 1 with a u, and I'm replacing my dx by a du over 2. And now, with a little bit of simplification, we can pull that 2 out front, and we're finding the integral of the sine of u du, and so we're just finding the antiderivative of sine. I can find the antiderivative of sine, which is negative cosine of u. Since we're doing an indefinite integral, we got to add our plus c constant. And now I'm going to go ahead and substitute my u back in, so I have 1/2 negative cosine of 2x plus 1 plus c. And if I simplify that just a little bit, I get negative 1/2 cosine of 2x plus 1 plus c. And that should be my answer. Now, we can do a quick check here. Let's say that our f of x is negative 1/2 cosine of 2x plus 1 plus c. So if I take the derivative of this, I get that f of x is equal to negative 1/2 times the negative sine of 2x plus 1. And now I need to multiply by a 2 here because I have a chain rule coming out of that 2x plus 1. Of course, we're going to get a plus 0 there at the end because the derivative of any constant is 0. And if I simplify that a little bit, these the negatives cancel out. So I have 1/2 sine of 2x plus 1 times 2. And now we can see that the 1/2 and the 2 also multiply to 1. So I have the sine of 2x plus 1. And that's a big check there because that is exactly our original function that we were trying to find the antiderivative of. So to recap, what we did is the reason that this antiderivative is a little bit hard to find is because this is a function that's going to involve some kind of a chain rule. So we can't just take the antiderivative as it's written. We need to do a substitution. So we're going to substitute out the very inside of the function, the 2x plus 1. We have to take the derivative of that function to get our du. We solve for dx to make our substitution of our dx really straightforward. Our substitution here is u. And then when we simplify, we get a really easy integral. And then to calculate that integral, we just do our regular antiderivatives, and we have to make sure that we substitute our u back in to get our actual antiderivative right there. All right, let's take a look at the next example. So for example B here, we have a little bit more complicated function. Now, after you practice this for a while, you're going to see that usually we're going to take the inside of the most complicated function as our u. So let's go ahead and start with that and see where that takes us. So we're going to have u is equal to 1 plus tangent of t. Now if I take the derivative here, du is equal to secant squared of t dt, or du over secant squared t is equal to dt. Now I don't see any secant squareds in the problem, but notice that I do have a 1 over cosine right here. So I can rewrite this as the integral of secant squared of t dt all over the square root of 1 plus tangent of t. And then I do have that secant both in my dt and in my original integrand that I should get to cancel out. So now let's go ahead and substitute some things in here. So I'm going to leave this secant squared of t, and then I have that dt is equal to du over secant squared of t. So that secant and that secant squared right there are both going to cancel out. And then I have the square root of u in the denominator. So we're going to get these secant squareds to divide out, which is really nice for simplifying this problem. All right, so one more step here. We have now du over the square root of u. It's kind of hard for people to keep track of when they're doing antiderivatives, so you might want to write that as u to the negative 1/2. And when we're going to find the antiderivative here, we're going to get u to the 1/2 over 1/2 plus c, which is equivalent to 2 square root of u plus c. And to convert that back to our x variable, we need to go look at our original substitution right here and plug that in for u. So we have 2 times the square root of 1 plus tangent of t plus c. And that's our final answer right there. Now, I want to take a quick second to show another way that you may have seen work being organized if you've ever seen U substitution before in other lecture videos or in another class maybe. So at the point where we've already rewritten this to secant squared of t dt over the square root of 1 plus tangent of t. Now, another way that people might do this is they might substitute directly from this du, because they see here that we have a secant squared t dt and we have a secant squared of t dt in the numerator, so that numerator can just become du. Now if we do the substitution that way, we get the integral of directly, we just get du right away, and then we have over the square root of u, which is the exact same thing we got by doing this roundabout way of substituting in our dt. Oh shoot, I forgot to write in there. Oh no, I have my du in there. And this is the exact same thing that we would have gotten by substituting in a little bit of a roundabout way. Now, why did I show you the way in blue first? Well, that's because usually when I've had people solve for dt, they're going to get the constant right more often. So if I scroll up here to the last problem, example A, a really common error is that students will get the integral of the sine of u times 2 du because of this 2 in the dx. So when I advise people to solve for dx and substitute that in, it'll get them to get the 2 in the denominator like it's supposed to be. So in example B, that's not as much of an issue because the substitution is direct. But when you're getting a constant, a lot of the times when you solve for dt like we did over here, you're going to get the constant in the right part of the numerator or the denominator by solving for dt. All right, let's take a quick second to jot down some of that work. All right, let's take a quick second to jot down that work. Go and pause if you need to catch up on any of this. All right, let's move on to example C here. Now there's actually two ways to do example C. We can either choose that u is sine or u is cosine, because we see here that if we chose u to be cosine, our du would have a sine in it. If we choose u to be sine, our du would have a cosine. I'm going to choose u equals the sine of x, because then I don't have to worry about the negative when I take the derivative right here. And again, I'm going to solve for dx by dividing that cosine of x to the other side. Now when we put our substitution in, we have that our u is our sine of x, and then we have our cosine of x here from the original integrand, and we know that dx is du over cosine of x. And so our cosines cancel like we want them to, and we're left with the integral of u du, which is a very easy integral to calculate. That's u squared over 2 plus c, and then we substitute our u's back in. We get the sine of x squared over 2 plus c as our final answer. So you can go and take a look at that work for just a second, and we'll move on to the next example. All right, let's take a look at the next example. So this is the webwork problem from the section 4.5 webwork, and it's number 2 in the webwork problem. So again, what we're going to want to do is we're going to want to choose our u to be whatever's inside of the most complicated part of the function. So we're going to choose our u to be 4 plus 11x to the 4th. And this problem is conveniently authored so that our du ends up having an x cubed term in it, which is important because that's going to cancel out this x cubed in the numerator. Now here's a case where solving for dx is going to really help us keep our work straight, because it's going to give us a 44 in the denominator to make sure that we get that lined up right. So let's go ahead and do our substitution. So we're going to keep that x cubed where it is, and then we chose our u to be the inside of that square root function, and then we have that our dx is equal to du over 44x cubed. Now we get the x cubes to divide out like we want them to, and we can see that we have a 1 over 44 as a constant that we can bring out front. And then we're finding the integral of du over the square root of u. So we have 1/44 times the integral of u to the negative 1/2 du. And when we find that integral, we're going to add 1 to the power. So we get u to the 1/2 over 1/2 plus c. And if we simplify that, we're going to get 1 over 44 times 2 square root of u plus c, which gives us 1 over 22 square root of u plus c. And to get this back into our x variables that we originally had, we can substitute our u back in, and we get the square root of 4 plus 11 x to the 4th plus c as our final answer for this example. All right, our next example is a little bit less friendly. So in example 13 here, we're pretty much left with, again, pursuing the root where u is equal to x plus 2, because that's what's inside of our most complicated function. That is the inside function that's put inside of this square root. And u substitution undoes the chain rule, and that's where the chain rule would have come into play. Now, du is just equal to dx, which is a little bit weird. So let's go ahead and substitute things in and see where we get. And we're going to run into a problem. So we have the integral here of x squared, square root of u, du. But now our problem is that we have an x squared left over, and it didn't cancel out. But this is the correct u substitution. So we have to play a little trick here. What we can do is, since we know that u is equal to x plus 2, we know that u minus 2 is equal to x, and then u minus 2 squared is equal to x squared, and that's the substitution that we're going to need to do. I'm going to simplify that one step further. U squared minus 4u plus 4 is equal to x squared, and that's what we're going to substitute in for that x squared over here on the left. So we have the integral of u squared minus 4u plus 4 times the square root of u du. Now this doesn't look much more simple, but this actually is a lot more simple because we don't have a function inside of the square root, which we don't know how to find the antiderivative of, but we can just use the distributive property here. So when we multiply this square root u to all three of these terms, we get u to the 5/2 minus 4u to the 3/2 plus 4u to the 1/2 du. And we can find that antiderivative quite simply by just adding 1 to each one of those exponents. So we get u to the 7/2 over 7/2 minus 4u to the 5/2 over 5/2 plus 4u to the 3/2 over 3/2, all plus c because we're finding antiderivatives. And now what I'm going to do is I'm going to go ahead and flip these fractions and plug our u back in all in the same step so we can fit this onto the next line. So we have 2/7 x plus 2 to the 7/2 minus 8/5 x plus 2 to the 5/2 plus 8/3 x plus 2 to the 3/2, all plus c. And that is our final answer for this problem. Now note, this problem is quite different from the rest of the problems in this problem set because we had to do this additional step where we needed to solve for x squared in order to substitute out that x squared term right there. That didn't cancel out when we substituted our u in and our du. So that's a little bit of a tricky problem. All right, let's take a look at example 14. This combines two different sections. It combines the last section that we covered, which is section 5.5, with the current section. The way that it does that is just by the initial statement of the problem. We need to find the average value. Well, what is the average value? Well, it's 1 over 3 minus 1, those are our bounds, times the integral from 1 to 3 of t over 3 plus t squared, the square root of that function, dt. And so finding this integral requires a u substitution. So what we need to do is we have that our u is equal to the inside of our complex function, so that is our 3 plus t squared, and that gives us that du is equal to 2t dt. Now again, we don't have a 2t in the numerator, so I'm going to go ahead and solve for dt so we make sure that we get our constant correct. So we have that dt is equal to du over 2t. Now let's substitute back into our integral. So we have 1 over 2, that's from that 1/3 right there, and then we have the integral from 1 to 3 of t over the square root of u times du over 2t. Now we actually have a problem here. These bounds, I'm going to go ahead and circle those because we have mixed variables here. In the original problem, this means from t equals 1 to t equals 3, but now that we're changing our variable to u, it's unclear what these bounds mean. They need to be corresponding to the integration variable, but they're still our old t values. So we're just going to leave those for right now. We're going to deal with that later and how we can change the bounds. But for right now, we're just going to continue this integration by converting to u, and then we're going to convert back to t's before we plug in our bounds. So we have 1/2, and then the integral from 1 to 3, and those aren't our t values, so we need to go ahead and circle those. And then we have du over 2 square root of u. And I'm going to go ahead and pull that 2 out, so I get 1/4 of the integral from 1 to 3. I'm going to continue to circle those because we still haven't taken care of those bounds yet. And then I have u to the negative 1/2 du. Now I'm going to calculate that integral. So I have 1/4, and then the antiderivative is u to the 1/2 over 1/2. And we're going to evaluate that from 1 to 3, but not really 1 to 3 because those are our t values, and we have our integral in terms of u. And so we get 1/4 times 2 square root of u evaluated from 1 to 3. And now what I want to do is I want to convert our variables back to our original t variables. So I get 1/4 times 2 square root of 3 plus t squared, and I'm going to stop circling our 1 and our 3 because those are actually t values and we can plug them into this antiderivative. So we have 1/4 times 2 square root of 3 plus 3 squared minus 2 square root of 3 plus 1 squared. And if we simplify that one step, we have 1/4 times 2 square root of 12 minus 2 square root of 4. And I could stop there, but I am going to go ahead and simplify this just one more step. So we get 2 square root of 12. I'm not going to rationalize that thing, but I do get a 4 right here, and that's a little bit easier to write. So that's going to go ahead and be our final answer right there for our absolute value, or our average value. We could have left this right here just when we plugged in our numbers, but that is our average value for this thing. So to recap, we needed to calculate the definite integral from 1 to 3, so we did our u substitution to find our antiderivative. But we had to keep track of the fact that while we had our u's involved, the bounds of the integral were not correct because those are our old t variables. So we needed to substitute back in for t in order to plug in the bounds of our integral. On the next problem, we're going to explore how to change the bounds. So for example 15 here, we're going to do the exact same integral twice. First, we're going to do it the way that we just did the last problem by finding the antiderivative of x and then plugging in our original x bounds. So what we're going to do here is we're going to have that u equals the cosine of x, because what we have here is the cosine of x squared sine of x dx, and the cosine function is inside of this composite function, so that has to be our u. Then our du is equal to the negative sine of x dx, or dx is equal to the negative, or is equal to du over negative sine of x. So when we go ahead and substitute this in, we have the integral from 0 to pi over 3. But we're going to go ahead and circle those bounds because those are our x bounds and we're changing to u. And so inside we have u squared sine of x, and then, so I've substituted the cosine for u, I left the sine of x, and then our dx is du over the negative sine of x, and we get those signs to cancel like we want. So we have the integral from 0 to pi over 3. I'm going to circle those still because those are our x variables and we are working with u's now. We have a negative u squared du. So I can find this antiderivative. I get negative u cubed over 3 from 0 to pi over 3, but those are not our actual bounds because those are our x variables. So we need to substitute back in our cosine. So we have negative cosine of x cubed over 3, and we're going to evaluate that from 0 to pi over 3. And now I can drop the circles on my bounds because I'm back in terms of x. To evaluate this indefinite integral, I'm going to go ahead and plug in pi over 3. So I get negative cosine of pi over 3 is 1/2. So I have 1/2 cubed over 3. And the cosine of 0 is 1. So, and I have 1 cubed over 3. And so I get negative 1/8 over 3 minus negative 1 over 3, which gives me negative 1/24 plus 1/3, which is like negative 1/24 plus 8/3, or 8/24, I'm sorry, I'm getting common denominators there. And so that gives me 7/24 as my integral. Now, let's explore how we can do the exact same problem, but we're going to change our bounds to help with our organization. So we have that u is equal to cosine of x, just like we did in the last problem, and then du is equal to negative sine of x dx. And again, dx is equal to du over the negative sine of x. Now, in order to change the bounds, I can evaluate my u at the boundaries to figure out what the boundaries would change to if we're writing them in terms of u. So u of pi over 3 is equal to the cosine of pi over 3, which is equal to 1/2. And then u of 0 is equal to the cosine of 0, which is equal to 1. So now what I can do is I can rewrite this integral with my bounds of 1 and 1/2 because I've converted my x bounds into u bounds by plugging them into my u equality for the x's. And then I have that cosine squared of x becomes u squared, and then I have sine of x times du over minus sine of x. And I get that we have the integral from 1 to 1/2 of negative u squared du. And we already found this antiderivative. It's negative u cubed over 3. But now I'm evaluating from 1 to 1/2 because I've already changed my boundaries. And that allows me to stay a little bit more organized. And when I plug in the 1/2, I get negative 1/2 cubed over 3, and when I plug in the 1, I get negative 1 cubed over 3, and what I have here is exactly what I had after I plugged in my bounds into my old x integrant. This is exactly what I had after I evaluated my antiderivative in the first example when I substituted back in for the x's. So we know that this is also 7/24, and they calculate the equivalent answer, but changing your bounds is a little bit more organized than substituting back for x before you plug in your x boundaries. Both of them are equivalent though, so you should do whatever makes the most sense to you. I'm going to pause here and let you copy down some of this work. All right, let's move on to the next example. So this is example 9 in the web work for 4.5. As we've been doing, we're going to choose our u to be the inside of the complicated function. In this case, our 25 minus 3x is going to be our u because that's inside of the square root. That gives us that du is equal to negative 3 dx, or dx is equal to du over negative 3. Now we want to change the bounds here since this is a definite integral. So let's go ahead and calculate u of 3, which is 25 minus 3 times 3, which is 25 minus 9, which is 16. And u of 0, which is 25 minus 3 times 0, which is 25. So when I convert my definite integral from x's to u's, I have to change the bounds. U of 0 was 25, u of 3 was 16, and then I'm going to rewrite my integrand using my u substitution. So I have 1 over the square root of u, and I have that dx is equal to du over negative 3. So I'm going to simplify this just one step. I'm going to pull that negative 3 out front, so I have negative 1 over 3, or I could have written that as 1 over negative 3. I think that's a little bit more straightforward. Times the integral from 25 to 16 of u to the negative 1/2 du. When I evaluate this antiderivative, I get u to the positive 1/2 over 1/2 evaluated from 25 to 16. It is a little bit weird that our bounds are a bigger number on the top and the lower number on the, or bigger number on the bottom and the lower number on the top. But that is the way that it works out. And this is being made up by this negative that we're getting from our du right here. So that negative counteracts the fact that these are going to be upside down and give us a negative integral. Let's keep simplifying here. So we have negative 1/3 times 2 square root u evaluated from 25 to 16. When I go ahead and evaluate at those boundaries, I get negative 1/3 times 2 square root of 16 minus 2 square root of 25, which ends up giving me negative 1/3 times 2 times 4 minus 2 times 5, which is negative 1/3 times 8 minus 10, which is negative 1/3 times negative 2, which gives me a positive 2/3 right there. And that's my final answer for this definite integral. Take a second and jot down some of that work. All right, we have one more page of examples, and these ones are a real doozy. This first one, example 16, isn't too bad. Now, the first thing that I need to do is I need to notice that I have the sine of 2x cubed right here. And that tells me that I need to have my u be the sine of 2x. So that my du is the cosine of 2x times 2, because I need to do a little chain rule right here, dx, or that du over 2 cosine of 2x is equal to dx. Okay, so now let's go ahead and substitute. We don't need to worry about u bounds because we have an indefinite integral here, so we're just trying to find the antiderivative. So I have that the sine of 2x is my u, so then if I have the sine cubed of 2x, that gives me u cubed. I'm going to go ahead and leave the cosine of 2x because we're going to want to cancel that out with our dx substitution. And I have that dx is equal to du over 2 cosine of 2x. And there we go. We got our remaining x variables to cancel out. So let's simplify one step here. We have the integral of u cubed times du over 2. And I'm going to go ahead and pull that 1/2 out front. And then we can just find the antiderivative of u cubed du. So we get 1/2 times u to the 4th over 4 plus c, which is equivalent to u to the 4th over 8 plus c. And that's our final answer, right? No, that's not our final answer. we need to convert back to x. And so we need to plug in the sine of 2x in for our u in order to get our antiderivative in terms of x, because our original function was in terms of x. If you wanted to, you could have written this as sine to the fourth of 2x over 8. Alright, this next example is already flagged as being an example that's quite tricky. So let's try to figure out what we need to do here. Alright, well, at first glance, you might think that we want x cubed to be our u, because the derivative of x cubed is 3x squared, and that might cancel out this x squared in here, but it doesn't because the x squared plus 1 is inside of the square root. So we're going to need to go with our usual strategy, and we're going to need to choose our u to be x squared plus 1, because that is what is inside of our square root function. And that gives us that du is equal to 2x dx, or that dx is equal to du over 2x. Let's go ahead and substitute these things in and see where that gets us. So if we have the integral here, I'm going to leave our x cubed right there. We have the square root of u, because that is our u. And then dx is equal to du over 2x. So we're going to be able to get one of these x's to cancel, but not both of the x, or not all three of the x's. So what we have here is I'm going to go ahead and pull out this 2 from that 1/2. So we have an integral of x squared square root of u du. And we didn't eliminate our x right there. So what do we need to do? We need to go look at our substitution and figure out if we can isolate an x squared in here. And we can. We have that u minus 1 is equal to x squared when we rewrite our initial u substitution. And that is what we can use to plug into this x squared. So if we do that, we get 1/2 times the integral of u minus 1 square root u du. And again, this doesn't look like it's simpler to integrate, but it's much simpler to integrate because we can multiply the square root of u to both the u and the -1. And when we do that, we get 1/2 times the integral of u to the 3/2 minus u to the 1/2 du. And that is something that we can find the antiderivative of. So you get 1/2 times u to the 5/2 over 5/2 minus u to the 3/2 over 3/2 plus c. Now, let's go ahead and substitute our u back in, and we get 1/2 times 2/5 x squared plus 1 to the 5/2 minus 2/3 x squared plus 1 to the 3/2, all multiplied by that 1/2 out front and added by the constant there at the end. So this problem is very difficult, and I anticipate that it's super confusing for you if this is the first time you've watched this video. But I think that this is where the advantage of solving for dx really shines, because it helps us cancel out one of those x's without having a full substitution ready for that x cubed. And that reveals that we're going to have this x squared term left over, so we know that we need to go look for the x squared in our original u substitution. Alright, we have one last problem for you. Example 18 here is a weird multiple choice question. We're trying to figure out this integral, the integral from 0 to 3 of f of x squared dx, given that the integral from 0 to 9 of f of x dx is equal to 4. So what we need to do is we need to change the bounds on the integral so we get the integral of our f of x function. So what we're going to try here is we're going to try our u substitution being x squared, because that is the thing that's inside of our function. If that's the case, then du is equal to 2x dx, and dx is equal to du over 2x. Now let's see where that gets us if we plug that in here. I have my integral let's go ahead and change our bounds as well. We're doing the integral from u of 0, which is 0 squared, which is 0, and u of 3, which is 3 squared, which is 9. And that's really ideal because that is the upper bound on our original piece of given information. So now we're finding the integral from 0 to 9 of, we're going to leave that x, and then we have f of u, and dx is du over 2x, and those x's cancel out. So we end up with 1/2, I'm pulling out that 2 in the denominator all the way out front, of the integral from 0 to 9 of f of u du. And like I said, and even though this looks like it's in terms of u and it doesn't match our initial piece of given information, these x's and these u's are just placeholders. So that is in fact a 4. And we get that 1/2 times 4 is 2. So our answer here is C. That's all we have for the 4.5 video. Now you should start on your web work, and you should definitely come ask me if you have any questions, because I know that this can be a little bit tricky at first. But once you figure out U substitution, it's a really powerful tool, and it's pretty straightforward. You're always just going to choose your U to be the complicated function that's in the inside of these composite functions. All right, we only have one more lecture video after this, section 5.1, so we're almost done with Math 132. Stay focused and keep working hard. See you all later.